Next, let's take a look at this guy down here. Now, if it's asking for a linear approximation, you guys know that if that's asking for the approximate change in f, which in our case is f prime of a times delta x. So we need to know a few things. We need to know what a is. We need to know what f of x is. That way we can find out what f prime of x is. And we also need to know what delta x is. So those are all the questions that should pop into your head when coming to this problem. Now look at this problem down here. Okay, what the crap will our, I shouldn't say what the crap, or what the heck will our function be?
E to the x, right?
Yeah, now I look at this part and I think e to the x. Now something that really helps me out is I know, when I see 0.1, I know what my a is going to be. Because this is really close to 0. And so I'm going to want to use 0. And what is e to the 0? 1. So it works. So I can rewrite this to make it, cleaner, I suppose, like easier to see, as e to the negative 0.1 minus e to the 0. Now it's obvious. Oh, my a, that's 0. My f of x is e to the x. The f prime is e to the x. Ooh, I like that one. And what's my difference? My change in x?
Negative
0.1. Now, change in x is always positive.
Oh, okay.
I think it's always positive. I'm going to double check on that.
Yeah, I think you told us that was positive.
Did I always say? I'm pretty sure it is. Okay.
It would be 0.1 minus 0 anyway, right? So it'd be just
Oh, yeah.
0.1.
Yeah. Okay. So then, actually, since it's the derivative is so simple, let's just finish it. Okay, we have the linear approximation is going to equal f prime of 0, which is e to the 0 power, and we're multiplying that times the change in x, which is 0.1. What is e to the 0 power? Oh, just 1. And so it's approximately equal to 0.1. Ooh, we're done. Man, that one was so pretty and nice.
It's negative 0.1 in the book.
And actually, yeah, thank you, Marwa. Okay, you're right. So the change is negative because it goes down. It's when you guys are calculating the error that you have to keep it positive. So that's negative 0.1. Okay? All right. So that's our linear approximation. Find the actual one. Well, we got to plug that into our calculator to find the actual one. Can you guys plug that in and find the actual? Tell me what it equals.
Plug what in?
Plug this right here. We go e to the negative 1 or 0.1, and you subtract 1 from it.
Negative 0.0951.
0.951? Is that what you got too, Veronica?
Yeah.
Okay.
Yeah.
So that's our actual one. Why do we need the actual one? We need the actual one to calculate our error. So we're going to take what we approximated and find the difference between that and what we approximated. So, and that's when you need the absolute value. So we need the absolute value of negative 0.1, and we're going to subtract from that the actual one that we found. So go negative 0.1 and add to that 0.0951. That is going to equal 0.0049. Now that's our error. Okay, but the problem with this is actually the error number isn't as useful as the error percentage. It doesn't ask for the error percentage, but let's do it just because it's that important. So it's 0.0049, and what you do to find the percentage is you divide it by the actual number. Our actual number in this case is negative 0.0951. I don't think the negative matters right now because we're finding a percent. So we're going to take that, multiply it by 100, and that's going to be our percent. So can someone do that? 5.6%. That's our percent error. This is our error, and this is our estimate. Finished.